Hello. So in the previous video, with some simulation experiments, I gave you three patterns, what like in the sampling distribution histograms, when you increase the number of dice, the sample size. So as I promised, I will make them into theorems. First one, the mean does not change, can be stated in this way: the expected value of the average equals the expected value of a single random variable. So single random variable is denoted without bar. So X just stands for one outcome, one single observation. So its mean determines the mean of the average, which is a very nice theory because you do not need to calculate the mean of the average again. And its proof is pretty simple, especially if I consider two cases, two sample size equals 2. Then first, we know that the mean of the first observation and the second observation are the same because they must be from the same distribution. Or you may understand it as the mean is not random, but the mean is common to the expectation is common to every observations. And then the expected value of the average can be written as the expected value of x1 plus x2 divided by 2, which is the definition of x bar. And then divide by 2 can get out of the expectation because it's multiplication of 1 over 2. And the addition of x1 and x2 also can be split into different expectations. So, and they are the same. So in the end, same thing has been added and divided by 2. So then it remains only one expectation. You do not need to know the proof. Just remember the outcome. And property number 2, the variance, I said parent number 2 is that the variability decreases as the sample size increases. And in particular, we can show that it decreases at the ratio of 1 over n. So the variance decreases at the order of 1 over n, but the standard deviation decreases at the order of 1 over square root n. So the left hand side is the variance of the sampling distribution, variance of the average, standard deviation of the average. And on the right hand side, this variance is for a single observation. So single observation variance, single observation standard deviation. So again, the property number 2 gives you the variance or the standard deviation of the sampling distribution as long as you know the variance or standard deviation of the single observation. And of course, the sample size is usually known. And you can show this in the simple case when n equals 2. Idea is the same. Variance can be written in this way. Variance of the average can be written in this way. But now remember, multiplication of 1 over 2 can get out of variance, but you have to square that. We learned it in chapter 4. So when you multiply something inside variance, you have to multiply its square outside the variance. So 2 squared, 1 over 4 is multiplied. And then two same variances are added. So one of the two, one is cancelled. So in the end, you only have 2. So 4, the denominator was 4, but numerator has 2 times variance. So cancelled out, but still there is 2 in the denominator. Again, the proof is not important. Just in case if you're curious and if it's more clear, then it would be nice to have a proof. But in case if you think it's useless, that's also actually not wrong. But the point here is the outcome. The outcome is simple enough, so you may not need the proof. And the third pattern is clear. The distribution of the average converges to a normal distribution as the sample size increases. This is really, really powerful. This is more powerful than the previous properties because it means that, like in the previous properties, you should know the variance or the mean of a single outcome. But property number 3 says that no matter what the distribution of a single outcome, the sampling distribution is normal. Really powerful. You don't need to know what happens in a single outcome. So, and we saw this from these experiments. Like the starting distribution is very, very weird. It's really weird distribution and many different types of distributions like these. But still, in the end, their shapes are the same. Of course, the variability and the center can be different, but the shape does not change. Basically, they are all following a normal distribution. So this is property number 3. So we formulated 3 patterns into 3 properties. They actually have more famous names. You may have heard about this, the law of large numbers. There are 2 fundamental theories in statistics. This is number 1, the law of large numbers. Given these the first 2 properties, what you can tell here is, so simply, the mean does not change. The conclusion is that the mean does not change, but the variance decreases. And in the limit as n goes to the infinity, in the limit, the variance of the sampling distribution will converge to 0. When the variance converges to 0 in the limit, that means there will be no randomness remains in the limit. Excuse me. Which means like if you are estimating something, your estimator will be perfect. There will be no error in the end, in the limit. So the more sample size you have, the more accurate and the less randomness there would be. That is the law of large numbers. As n goes to the infinity, the randomness in the average disappears and x bar converges to the true mean, right? So probability will disappear everywhere else but the center. In the end, the probability will be more and more concentrated as n goes to the infinity. In the end, it will collapse down to 1 point. So there will be simple spike in the end, in the limit, theoretically. So it means you may understand it as no randomness, which means no error. It's 100% accurate, no uncertainty. So that's the meaning of the law of large numbers. And the property number 3 is called the central limit theorem. Maybe you may have heard about these 2 theories. This is the second fundamental theory in statistics. Central limit theorem is exactly what I said earlier. So for sufficiently large n, as n goes to the infinity, x bar approximately follows a normal distribution. And what are the parameters? The parameters are already given by the first 2 properties. The mean, the parameter of normal distribution is mean and variance. But mean is the same as the mean of single outcome. So here, this is the expectation of a single outcome. And the variance is inversely proportional to the sample size. And numerator has the variance of a single outcome. So we know, if you know the mean and variance of a single outcome, you know the approximate sampling distribution. You can approximate the sampling distribution by normal distribution, which we know. We studied how to calculate the probability, any probability for a normal distribution, even if they are not standard, right? We did that in the previous chapter. So the purpose of chapter 6 was to understand this distribution, right? So sampling distribution. And then usually a natural question is, okay, the theory is saying like n converges to the infinity, but in practice, we never have infinity. And then then how many sample size do we need to have? There is no clear-cut answer. There is no scientific answer. But textbooks say 30 or 35 would be large enough. But there is no clear threshold. If there is more noise, then 35 may not be enough. If there is like less noise, then 20 could be enough. Like as you see in here. And can you agree that it is a normal distribution? Like, to be exact, it's not a normal distribution. There is a jump. It's smooth, approximately smooth, but not perfectly smooth. So it's just like a subjective judgment. Like, is this a normal distribution? Is that a good approximation? No one can say that, but consensus is around 30 or 35, and this is, I think, the bare minimum. And usually, I would recommend you to have at least like 100 observations. And these days, having 100 observations is not that difficult, right? These days, we are living in the age of data, big data. So 35 is a joke, right? If you have only 35 observations for some analysis, then no one is going to believe that. It's too small sample, right? So the simple conclusion is the more the better. So try your best to collect the most observations as much as possible, right? So anyhow, we learned two basic fundamental theorems: law of large numbers, central limit theorem, CLT, and LLN. And I will show you how to utilize these two guys. So think about the earlier example. We considered surveying 1,000 people's annual income, and so we know that the mean of the overall, so the average income in the United States is $50,000, and the true standard deviation of income in the United States is, say, $10,000. But we know the mean and the standard deviation from the census data. Census does not ask income, but just suppose there, like say from IRS. IRS has full data set about income, so IRS tells you the mean and the standard deviation, but you don't know the exact distribution of the income. There are Bill Gates, Jeff Bezos, Elon Musk, Warren Buffett, who are extremely rich. So the distribution cannot be normal. It's usually positively skewed, like a longer tail on the positive side. And in this case, if an economist surveys 100 people and calculate their average, then what is the probability that the economist underestimates the average income by more than $3,000? So this is what you can do. Because we know the true mean and the true standard deviation, and we studied the sampling distribution earlier, so we can calculate the probability of the randomness in the accuracy, the probability about how accurate survey can be, right? That's how we utilize statistics in real analysis. I'm going to give you the exact answer to this topic in the next video. So see you in the next video. Bye.